This video will cover the RETScreen project feasibility analysis based on a study for a 500 kilowatt small hydro run-of-river project at an existing dam in Ontario, Canada. The study will use a method 2 type of analysis and cover the energy model, cost analysis, emission analysis, and financial analysis worksheets. To begin, we'll provide a brief comparison of analysis types method 1 and method 2 on the start page. In RETScreen, selecting method 1 next to analysis type offers a simplified way of doing a basic or pre-feasibility analysis. When hydro turbine has been selected as the technology, the differences between method 1 and method 2 are essentially related to the number of input fields available, especially under the cost analysis section. Under method 1, a much reduced and simplified cost analysis is incorporated into the financial analysis section, and there is no option for risk or sensitivity analysis. Selecting analysis type method 1 is very useful if very limited initial and operating cost information is available, or if these costs are already known and we are mainly interested in analyzing changes to other aspects of the model. However, under method 2, we have the opportunity to enter the same basic cost information and to break down the cost into a greater number of cost items. This ability renders the method 2 option more practical and therefore will be used as the basic analysis option for this assignment. Let's consider the project location. The dam is located near the village of Plainfield on the Mora River in central Ontario, in Canada, and the project is situated near existing roads and the central grid. The Mora River is a regulated river with numerous dams used for flow control, water level management, and ice control during the spring thaw. Although there is a small dam at the site, it is not used as a reservoir for water storage, and the project will be operated as a run-of-river basis. The dam was originally constructed to divert water to power a mill, built on the east bank of the river. Remnants of the mill's carriage house remain on the west bank. At the time the study was undertaken, the dam was in poor state of repair, with the original turbine and housing destroyed during a major flood. Dam renovation work would therefore need to be made as part of any hydropower redevelopment. Let's open RETScreen version 4 and enter the basic data in the start page. First, we'll enter the project name, which we will call Low Head 500 kilowatt Small Dam. Next, we will enter Plainfield, Ontario, Canada as the project location. In the Prepared for cell, we will type Leonardo Energy, and you will enter your own name in the Prepared by cell. For project type, let's select Power, and for technology, Hydro Turbine. The project would also be connected to the central grid. For reasons explained previously, we will select method 2 as the analysis type. Note that we would select higher heating value, or HHV, as the heating value reference because the project is located in North America. This is the energy per unit weight of fuel that is measured by an oxygen bomb calorimeter. The HHV includes the energy available when the water vapor in the combustion product is condensed. This energy is not really available in any practical combustion system, so using the HHV gives a false indication of the energy that is actually available from the fuel. Outside of North America, the lower heating value, or LHV, is used, and this value does not include the energy from condensing water vapor. In order to pick the most appropriate location, we will use Google Earth. Google Earth can be downloaded free from earth.google.com. The site coordinates are latitudes 44.301 degrees north and longitude minus 77.339 degrees east. Let's go to that location by typing 44.31, minus 77.339 in the Google Earth search box, then press enter. This takes us to a location about 16 kilometers north of Belleville and just north of Plainfield. The map shown here contains a custom placeholder that we have created to be able to identify the site on the following maps. The RETScreen Plus software provides a better search functionality for locating the nearest weather station. RETScreen Plus is installed automatically when RETScreen Suite is installed. Let's start the RETScreen Plus application by using the icon on your desktop or by clicking on the RETScreen Plus item under the RETScreen group on the Start menu. Click the Select Climate Data Location tab and then use the search box to type Plainfield, Ontario in Canada and then press enter. This zooms in on the area of the project. Drag the project location icon in the box titled Site Reference Conditions to the area of the project. This displays the latitude and longitude of the icon and closest to that location as shown here. If we zoom out from that map, we can see that the Trenton Airport is the best match for that location, both in terms of distance and in terms of possible microclimatic factors. Since we already used RETScreen Plus to identify the best match for the weather station, we can now close RETScreen Plus and return to RETScreen 4. By default, RETScreen uses the climate data from Ottawa, Canada. To see that data, click on the Show Data checkbox as shown below. Let's change the RETScreen climate data by clicking the Select Climate Data Location link. After selecting Canada as the country, let's select Ontario as the province. After this, we select Trenton Airport as our climate data location. We should see a dialog box as shown here. To confirm that we want to use this data, let's click the green check icon. Next, in the RETScreen Start Worksheet, let's click the Show Data checkbox. The climate data table shows the climate data for the Trenton Airport. Let's now go to the Energy Model tab. We will go directly to the proposed case power system as the project would be grid connected. The technology value is automatically set to hydro turbine. For the Energy Model Analysis type, we will conduct simplified analysis. Let's select Method 1, which will reduce the energy model to a few input fields. For power capacity, if we select a Method 2 analysis, a hydrological analysis would need to be conducted to help us determine the optimum turbine capacity to use. For this study, a 500 kilowatt turbine is considered. Let's enter 500 as the capacity value. The product database offers a number of manufacturers and model options. In this case, the turbine manufacturer is not listed. Let's enter MJ2. For the model type, we will enter DN4500. The capacity factor represents the ratio of the average power produced by the power plant over a year to its rated power capacity. If Method 2 was selected, the resource assessment and technical analysis would calculate the capacity factor automatically. Typical values for hydro plant capacity factors range from 40 to 95%. For a selected river with a given hydro system design, the higher the design flow, the lower the capacity factor. Provided that there are no restrictions on the maximum output of a hydro plant, the optimum size of the plant will depend primarily on the availability of water. At some point, the cost of building a larger plant cannot be justified by the resulting increase in energy production. Typically, for a run-of-river hydro plant, this point is usually close to the mean flow at the site. If a more complete hydrological analysis was done, it would show a flow duration curve with a high spring runoff and very low summer flow, which would be indicative of a low capacity factor. However, As the river is regulated, a somewhat higher value is reasonable. If the dam had storage capacity, the capacity factor could be higher. However, the operation is run-of-river, so we will enter 60%. In the next cell, the electricity exported to the grid is automatically calculated. At the time the original study was conducted, Ontario was in the midst of its feed-in tariff program, whereby a small hydropower producer could get paid 13.1 cents per kilowatt-hour delivered to the grid. So in equivalent megawatt-hours, we will enter $131 per megawatt-hours, which will be our electricity export rate. The model should now look as follows. Let's now go to the next worksheet by clicking the Cost Analysis tab. We'll use method 1 as this is appropriate for our first approximation. We then get the following breakdown. Once a potentially cost-effective proposed case project has been identified through the RETScreen pre-feasibility analysis process, a more detailed feasibility analysis study is often required. This is particularly the case for large projects. Feasibility studies typically include such items as site investigation, a resource assessment, an environmental assessment, a preliminary project design, a detailed cost estimate based on quotes, and possibly a greenhouse gas baseline study and monitoring plan, all summarized in a feasibility report. Feasibility study project management and travel costs are also normally included. Hydro feasibility studies typically cost about 1 to 5% of the total project cost. For very small projects, the cost of the more detailed feasibility study relative to the cost of the proposed case project might not be justifiable to the buyer and is sometimes credited back to the developer if the project gets approved. In this case, the project proponent might choose to go directly to the engineering stage. Sometimes, with very small residential scale projects, a client might not require a feasibility study and will only ask for a proposal from the supplier, relying on the supplier's preliminary analysis of energy savings estimates and price quotation. Note that the RETScreen Clean Energy Project Analysis software can also be used to help prepare the feasibility study. Under Method 1, there is only one field to enter for feasibility. However, it is useful to keep in mind that there are a number of tasks normally associated with project conception and feasibility. These include a resource assessment, site investigation, evaluation of interconnection options, fatal flaws review, grant research, and application development, environmental assessment and regulatory aspects, cost estimates, and conceptual design. While medium and large-scale projects will often call for detailed feasibility studies, small-scale projects rarely merit the level of detailed analysis typical of such studies. Occasionally, very complex small projects may warrant detailed feasibility studies as well. As this is a small-scale hydro project, we will enter $50,000 as we expect it to be the appropriate cost of a feasibility study for this type of project. Once the feasibility study has identified the proposed case project as desirable to implement, project development activities follow. For some projects, the feasibility study, development, and engineering activities might proceed in parallel, depending on the risk and return acceptable to the project proponent. Estimating the cost of the development phase depends on the particular development arrangement established. Under Method 1, there is only one field to enter for development. However, it is useful to keep in mind that there are a number of tasks normally associated with this stage, including contract negotiations, permits and approvals, site survey and land rights, greenhouse gas emissions validation and registration, project financing, legal and accounting, project development management, and travel costs. Similar to requirements for feasibility analysis, development activities are much more pertinent with large projects that require a number of non-construction related managerial activities. Most hydro projects have substantial development cost, even small projects, and we can enter a cost of $150,000 here. The engineering phase includes costs for the proposed case project site and building design, mechanical design, electrical design, civil design, tenders and contracting, and construction supervision. If the project is awarded on a design-build basis, then all of these costs would be included in prices provided by the equipment supplier or contractor responsible for the project. If the project is awarded by tender based on specifications prepared by a consultant, then there will be engineering charges from the consultant overseeing the project and perhaps the equipment supplier. Higher projects usually involve substantial engineering cost, even for small projects. In this case, we'll also need to allow for some engineering costs for refurbishment of the dam. Under Method 1, there is only one field to enter for engineering. Here, we'll enter $200,000 for the total estimated engineering costs. The hydro turbine unit cost cell allows us to enter the installed cost per unit capacity for the proposed case power equipment. The capacity is copied automatically from the energy model worksheet to the cost analysis worksheet. This value includes both equipment and installation cost. Typically, due to economies of scale, the larger the capacity, the lower the installed cost per unit capacity. While typically out of date and incomplete, the RETScreen product database contains some supplier contact information that may be useful to obtain power equipment and installation prices or other information required. The power system, as defined here, includes the hydro turbine, the associated road construction, transmission line, substation, and power-related energy efficiency measures cost. The typical average cost for hydro equipment can vary considerably depending on the project location, scale, and type. However, a figure of $2,500 per kilowatt can be considered as an appropriate baseline. In this case, the turbine and generator are not customized for the site, but rather obtained as one standard pre-manufactured unit, which results in lower cost. The MJ2 VLH DN4500 turbine with integrated generator and controls can be supplied for a cost of $1,900 per kilowatt, which is the cost we will use. An access road for construction and ongoing service road are normally required for medium to large scale power project. These requirements will depend on the site selection and the nature of the terrain. There might be seasonal limitations for both construction activity and for use of roads to transport equipment. At some project sites, there may be no need for road construction, even if the site selected is not located on existing routes. However, the location of the existing roads should be a consideration during site selection. The cost for road construction typically ranges from $0 to $80,000 per kilometer, but can be as high as $500,000 per kilometer where river crossings are required. The length of the road required comprises the length of the access road to the site and the length of the service road on the site. The anticipated length of the required access and service roads can be determined by topographic maps. The site is located near existing roads and on a permanent access road of approximately 500 meters is required. So we will enter 0.5 as the quantity in kilometers. The estimated cost is $40,000 per kilometer, which we will enter as the amount. Note that the RETScreen input value does not display decimal in the cell itself, only in the formula bar, so we'll need to double check that the correct values have been entered. The transmission line cost is site-specific and depends on the type, length, voltage, and location of the line, and the installation capacity of the power plant being deployed. The estimated transmission line and substation cost table provides an indication of the approximate costs involved, assuming reasonable access. These 2006 costs are representative of aerial lines in North America and should be adjusted based on site considerations. Underground lines are normally used to connect the system within an urban area where the cost can be 2 to 4 times higher than an equivalent aerial line. Typically, 25 kilovolt transmission lines will be used for distances shorter than 50 kilometers. 44 kilovolt transmission lines will be used for distances between 50 and 70 kilometers, and 115 kilovolt transmission lines will be used for distances longer than 70 kilometers. The transmission line cells allow us to enter the length of the transmission line and the cost per unit of length. In areas of permafrost, special soil conditions can increase the cost of line extensions significantly. Advice from an expert specializing in local transmission line design or construction might be required in order to estimate the cost. In order to better evaluate the cost, let's go over power distribution fundamentals. Distribution is the local electrical infrastructure through which electricity is delivered from the high voltage regional system to the end-use electricity consumers. Distribution is generally characterized by short-distance lines, low-medium capacity transformation and switching stations, and typically a low degree of meshing of lines and stations. Most end users of electricity are supplied from the distribution system. The distribution system is radial in nature. Loop feeds are primarily reserved for areas of high density. Distribution assets are those wire assets downstream for the high voltage network and connection assets. Traditionally, distribution assets include stations and single circuit lines or feeders, which are operated at less than 50 kilovolts. Typically, distribution stations have 2, 3, or 4 feeders to distribute supply to retail customers and end users. DS transformer protection is local and provided by fuses or circuit switchers. Distribution feeders are supplied through reclosers or fuses. Generation connected to the distribution system is typically less than 50 megawatts in capacity, and the electricity produced is locally consumed. Since this project is a small-scale on-grid project connected to the distribution system, and the grid connection point is 500 meters away, we will enter 0.5 as the distance of transmission line in kilometers and a cost of $75,000 per kilometer. The substation cost is site-specific and depends mainly on the voltage and the installed capacity of the power plant being developed. Auxiliary electrical equipment might also include such items as dump loads and heaters, banks of capacitors, monitoring equipment, and integrated or SCADA type control systems. Here, we could also calculate the total itemized cost for related equipment based on the substations and other auxiliary electrical equipment. For smaller scale projects close to the electric distribution grid, substation costs will likely be lower than presented in the table. A more exact substation cost can only be obtained once electrical engineering tasks have been done and an interconnection estimate has been obtained from the local utility. At this stage, we will enter an expected cost of $250,000. User-defined field cells can be used to enter any expected additional costs or credits. For this project, it is anticipated that additional civil work cost will be required to construct the housing structure for the turbine. As repairs to the existing dam will need to be done, we can group these costs with the turbine powerhouse. If it was separate, we could enter the dam repair cost under the balance of system section. Let's change the cell labeled user defined to read civil work and enter an amount of $500,000. The balance of system and miscellaneous cost for the proposed case project typically includes a number of items such as specific project cost, building and yard construction, spare parts, transportation, training and commissioning, contingencies and interest during construction. Under Method 1, the number of input fields is reduced to spare parts, transportation, training and commissioning, contingencies, interest during construction, and one user-defined field. The cost for spare parts necessary for the proposed case project should be included in commercial scale or larger type of project budgets. The after-purchase price will most often be significantly higher. The extent of the inventory required will depend on the reliability of the system, warranty, complexity of equipment at the site, transportation difficulty, and availability of off-the-shelf components. For smaller systems, the cost of spare parts is normally part of the purchase price request to the manufacturer. The supplier would need to be contacted in order to obtain prices or other information required for a more detailed feasibility study. The cost allocated to spare parts is best described as a percentage of the total system cost. For large projects operating in normal conditions, an inventory of spare parts representing at most 3% of the total equipment cost should suffice. For very small projects, the cost of initial spare parts could represent up to 30% of the total equipment cost. Since the generator is an off-the-shelf unit, lower than average spare part costs are expected to be required, so we'll assume a modest value of 10%. Transportation costs for the equipment and construction material will vary widely depending upon the mode of transport available and the location of the project site. In many instances, the cost will depend on the transport distance and be based on a volume-weight formula. Costs to handle the material at the receiving end should also be considered. In very isolated and remote areas, bulk shipments might be received once a year, and logistical control is extremely important here. Shipping costs should be obtained from shipping agent when the scope of the project, equipment and materials are determined. Note that the transportation costs might also be included in the equipment cost entered previously. For this project, the key equipment would be shipped from France to Montreal, Canada, first by rail and then by road to the project site. Other material can be sourced within Ontario. For this, a cost of $30,000 is expected. The adequate training of operators and maintenance personnel is fundamental to the successful deployment of any technology. The costs associated with the training of equipment operators and maintenance personnel will depend on the size, complexity, and remoteness of the project. For isolated areas, there will be a greater need for locally trained technicians in order to avoid lengthy repair delays. Commissioning is the last activity of the construction phase. It consists of operating all of the equipment to detect and fix any malfunction and ensure that the plant functions as guaranteed. Commissioning normally involves the monitoring of the equipment performance over a set of period of time under typical operating conditions. The costs associated with the commissioning of the project will depend on the technology, size, and number of systems implemented, and on the skills and experience of the operations and maintenance staff. It could also depend on the climatic conditions to the extent that a sustained period of peak heating or cooling load is required to demonstrate and prove the adequate performance of the equipment. For small systems, this cost will likely be insignificant. Most small hydro stations have two types of operators involved, on-site and remote. Only very small hydro projects are not automated these ways. For this project, we can expect that one operator will remotely monitor the performance of the project equipment from a computer, and one local operator close to the project area might visit the site on a daily or weekly basis for maintenance purposes. Both operators need to be trained. Commissioning involves a short testing period to ensure that everything is operating according to plan. The total for training and commissioning is therefore estimated at 5 days with $1,500 per day. The allowance made for contingencies work depends on the level of accuracy of the cost estimates. Contingencies are estimated based on a user-selected percentage of the subtotal of all project costs, excluding interest during construction. Note that the contingencies are incremental in the sense that they are derived from project cost, including any credits. The allowance for contingency item should be based on the level of accuracy associated with the estimate of the project cost. Typically, a pre-feasibility level cost analysis should be accurate within plus or minus 40 to 50%, and a feasibility level analysis should be accurate within plus or minus 15 to 25%. However, this accuracy will depend on the expertise of the study team, the scale of the project being considered, the level of effort put forward to complete the pre-feasibility or feasibility study, and the availability of accurate information. Contingencies for hydro projects can be substantial, as there are many unknown factors that are usually only discovered on-site. For this project, however, we have a firm cost for generating equipment and a reasonable expectation as to what the expected dam repairs cost will be. However, adequate provision of funds to handle budget overruns should still be made, so we will use 25% as a contingency to offset such possible risks. Interest during construction will vary depending on the duration of construction and the cost of money. Here, we will enter the interest rate and the length of construction in months, which represents the length of time between building and infrastructure construction, delivery of the equipment, and commissioning of the system. The interest during construction is then calculated assuming the average debt over the project length in months is 50% of the subtotal of all project costs. For example, if $1 million worth of equipment must be financed over 12 months at an annual rate of 10%, we should enter 10% as the interest rate during construction. This would give us a calculated interest cost during construction of $50,000. The cost of interest during construction can vary between 3 and 15% of the project costs. For this project, the developer is pre-approved for financing at a 7% interest rate, including interest during construction, and the period of equipment assembly and construction is expected to be 6 months. Let's enter this information into the appropriate cell. Overall, given the cost analysis, the total price is $2,912,594 for a 500 kilowatt system, or $5,825 per kilowatt. Compared to other small hydro projects, the cost is well within the expected range. As a standalone project, this project would not benefit much from the economies of scale we can expect for larger projects with higher capacity. However, if a series of similar dams on the Mora River was done at the same time, some cost savings might be possible. A summary of the initial cost is displayed here. Let's explore the annual cost items. The parts and labor cost item summarizes the cost of spare parts and annual labor required for routine and emergency maintenance and operation of the proposed project. It also includes the transmission line and the district heating or cooling network maintenance. Operation typically includes activities like monitoring, regular inspection of the equipment, snow, ice, and dirt removal, and scheduled maintenance. When the maintenance of transmission lines associated with a power project is required, it may involve periodic clearing of trees or replacement of parts that become damaged due to lightning, impact, or other causes. The annual cost of transmission line maintenance is often estimated based on the capital cost of the transmission line and substation. For utility-scale projects, annual costs normally range between 3 and 6% of capital costs depending on the location and communication equipment required. Labor costs in isolated areas are typically twice the rate for urban locations in the same country. In these isolated areas, productivity is often less, as resources are limited, and an annual allowance should be made for travel and accommodation costs associated with annual maintenance. The costs proposed should thus be adjusted accordingly if appropriate. There will be a number of annual costs associated with the operation of a proposed case project. These could include operations and maintenance savings or cost, land lease and resource rental, property taxes, an insurance premium, parts and labor, greenhouse gas monitoring and verification, community benefits, and general and administrative expenses. In addition, costs for contingencies and fuel consumption for the proposed case can also be incurred. For hydro projects in North America, the cost of labor can range between $40,000 and $80,000 per person year in 2010. The number of person year of labor can range from 0.2 to 1.0 and will depend on the degree of automation built into the hydro plant. For this project, we anticipate using 2 part-time operators at $20,000 each and an additional $20,000 for parts. So we'll set the quantity to 3 and the unit cost to $20,000. The bed of the river is located partly on Crown land, which in the province of Ontario requires any hydro generating station to pay a water rental fee to the Ministry of Natural Resources, equivalent to 9.5% of the gross annual income of the plant. We will change the user-defined label under the OEM to read MNR Water Lease. Set the quantity to 1 and set the unit cost cell by typing equals, then clicking on the financial analysis at the cell that contains the gross annual income, which is located at K31, then by multiplying that by 9.5%. This will enter equals apostrophe financial space analysis apostrophe exclamation mark K31 star 0.095 in the unit cost cell, which would automatically calculate the new value from the financial analysis sheet if the annual income was to change. An annual contingency allowance should be included to account for unforeseen annual expenses and will depend on the level of accuracy of the operation and maintenance cost estimate section. This is especially true in the case of projects located in isolated areas. It is common to carry a contingency allowance equal to the replacement cost of the most expensive component subject to catastrophic failure. The contingency allowance is calculated based on an estimated percentage of the other operation and maintenance cost. It typically ranges from 10 to 20% of these costs. Given that the main project components are off-the-shelf parts with known operation and maintenance schedules, the unknown aspects are related to the project location. We will therefore set the contingency cell to value of 10%, which should be reasonable based on these factors. Under method 1, we have fewer number of fields to enter cost compared to method 2. 2 user-defined fields and 1 end of project life field. The periodic cost section is provided to allow us to specify the recurring costs associated with the operation of the system over the project life. Gray input cells are provided to allow us to enter the name of a periodic cost or credit item. Periodic costs represent costs that must be incurred at regular intervals to maintain the project in working condition. The description of the periodic cost item is entered in the gray input cell. We then select cost from the drop-down list in the unit column. The interval over which the periodic cost is incurred is entered in the year column. The amount of the cost incurred at each interval is entered in the unit cost column. The project may also be credited for periodic cost that would have been incurred over the project life of the base case or conventional energy system. The periodic credit item is entered in the gray input cell. When applicable, select credit from the drop-down list in the unit column. The interval over which the periodic cost is incurred is entered in the year column. The amount of the credit incurred at each interval is entered in the unit cost column. Note that the credit item is expressed as a negative value in the amount column. The periodic costs associated with the project are anticipated to be attributable to major maintenance and repair of the generation equipment, as well as dam maintenance and repair work. Let's change the first user-defined label to turbine and generator. Given the manufacturer's recommended maintenance schedule, let's also enter the year value as 15 and a unit cost of $75,000. Major civil work-related maintenance and repair work is not expected to occur within a short period after construction, but costs can be more substantial. Let's label the second user-defined cell as dam and other maintenance and assume an expenditure occurring in year 21 with the corresponding unit cost of $200,000. The end of project life row is used to enter the residual or salvage value of the project at the end of its life. If the salvage value of the project at the end of its life is positive, then select credit from the drop-down list in the unit column in order to express this item as a negative value. However, if the cost of remediation or decommissioning that must be incurred at the end of the life exceeds the salvage value, then we must select cost from the drop-down list. Hydro projects frequently have long operating lives, 80 years being typical. For this study, a 40-year term equal to the power purchase agreement has been used, so a considerable residual value will remain at year 40, and the whole project or just the equipment could be sold. Thus, we'll assume a credit amount with a negative unit cost of $1 million. Let's now go to the next worksheet by clicking the Emission Analysis tab. To perform the RETScreen emission analysis for the project, we first need to define the baseline electricity system. We can select the type of analysis from 3 different options. Method 1 is a simplified analysis of greenhouse gas or GHG emissions. Method 2 uses many predefined parameters in the calculations, and Method 3 requires that we enter these parameters ourselves. We would typically select Method 1 if electricity generation emission factors provided by RETScreen for the country region were up to date and representative. GHG emission factors for electricity generation for some jurisdictions might be calculated on an aggregate basis to help simplify the preparation of GHG calculations. The simplified Method 1, used for calculating the baseline for a project, can reduce the time and costs associated with establishing the baseline for the project, but in most cases will reduce the accuracy of the baseline calculations. RETScreen includes electricity generation GHG emission factors for most countries as of the last time RETScreen updated the data. If we selected Method 1, we would have to select Canada, Ontario as the country region for the drop-down list. RETScreen includes electricity generation's GHG emission factors for the year 2005 for all Canadian provinces and territories, and for a number of countries and sub-regions. Note that GHG emission factors will vary from year to year and from fuel to fuel. RETScreen does not take into account the fact that for large hydro using dams, for about 30 years after flooding the area used as water reservoirs, and that have vegetation, this potentially creates just as much GHG emission as GHG from natural gas power plants. Similarly, while RETScreen assumes that nuclear does not create GHG emission, this does not take into account GHG from mining uranium, transport, and the use of GHG-intensive concrete for storing nuclear fuel waste. Transmission and distribution, or T&D losses, are not included in these factors and would have to be added separately. When readily available, up-to-date information should be used. However, in the absence of other data, this country region information can be used to provide a very rough first estimate. All types refers to all fuels on the grid. We can also select natural gas, coal, oil number 6, or other, depending on the fuel displaced by the proposed case project. In reality, we would want to consider not the average mix of energy that makes up the grid mix for that region, but rather the type of fuel that would be displaced by the hydro project. If we select method 3 for the emission analysis, we can see the following grid mix, which is roughly what RETScreen would use, unmodified, when method 1 is selected for Ontario, Canada. As shown in the figure here, the scenario in 2012 has changed significantly from the outdated snapshot provided by RETScreen. What is more, not only has the Ontario government effectively reduced the percentage of coal supplied power to approximately 2.8% of the energy mix in 2012, but it appears to be on track with its goal to end coal power generation by the end of 2014. In that context, coal would go from almost 34% to virtually nothing over the life cycle of this project. When electricity is produced from this small hydro facility, it is likely that no nuclear plant will be shut down, as shutting down a nuclear plant is a longer and complex process. This is why nuclear energy, which runs day and night regardless of the load, is called base load energy. Small hydro and small-scale renewable energy is not considered base load generation and does not compete for the same loads. When loads fluctuate, dispatchable generation is used. Dispatchable generation refers to sources of electricity that can be dispatched at the request of the power grid operator, that is, generating plants that can be turned on and off or can adjust their power output on demand. This is to be contrasted with certain types of baseload generation capacity, such as nuclear power, which may have limited capabilities to maneuver or adjust their power output, or variable renewable energy sources, such as wind power, which cannot be controlled by operators. The time periods in which a dispatchable generation plant may be turned on or off may vary, and be considered in time frames of minutes or hours. For example, the 1.7 gigawatt Dinorwing pumped power station in the UK can reach full output in 16 seconds. It is also important to note that most large-scale renewable energy systems, such as large wind or solar farms, are set up with power purchase agreements that guarantee the purchase of energy regardless of load fluctuations. In Ontario, hydropower has traditionally been cheaper than natural gas power, and in the next 20 years, this is likely to still be the case. So the energy source that would likely be reduced as a result of this hydro project would be natural gas power plants feeding the grid, as the grid operator gives priority to the power obtained from the cheapest source of electricity. Let's make sure we have changed the emissions analysis type back to method 1 And then for fuel type, let's select natural gas. The GHG emission factor used here excludes transmission and distribution (T&D) losses for the base case electricity system specified. We can obtain GHG emission factors by selecting the country, region, and fuel type in the two adjacent cells to the left. If a blank value appears, that indicates that no information is available for that selection, and we can override these values by entering a value directly in the cell. Under Emission Analysis Method 3, if we set the T&D losses to 0% for natural gas, this results in a value of 0.439 ton CO2 per megawatt hour. So, referring back to the Method 1 emission analysis, we will set the GHG emission factor to a value of 0.39 tons of CO2 per megawatt hour. We can choose to express the emission factor in kilograms of CO2 per kilowatt hour or in tons of CO2 per megawatt hour, which are equivalent. For example, if we click on tons of CO2 per kilowatt hour under GHG emission factor, or use the drop-down list to switch to kilograms of CO2 per kilowatt hour, the model returns a value of 0.439 kilograms of CO2 per kilowatt hour. The T&D losses cell of the base case electricity system is used to enter all the percentage of energy losses between the power plant and the end user. The value will vary based on the voltage of transport lines, the distance from the site of energy production to the point of use, peak use energy, ambient temperature, and electricity theft. In addition, T&D system type and quality may also influence losses. The model calculates the weighted average of the T&D losses of the global electricity mix on the bottom row of the table. Units are given as a percentage of all electricity losses to electricity generated. As a first estimate, it is reasonable to assume T&D losses of 6 to 10% in modern grids in industrialized countries and 10 to 20% in grids located in developing countries. Considering the fact that natural gas plants in Ontario are made up of only a few very large operations that serve a very vast territory, we can assume the T&D losses to be at the top of the range. We'll assume the T&D losses at a value of 10%. The model calculates the GHG emission factor for the electricity system specified. The value is calculated based on the GHG emission factor and the T&D losses you have entered. In our case, we get a value of 0.488 tons of CO2 per megawatt hour, which is about half a ton per megawatt hour. By ticking the box, we can indicate whether or not the baseline changes during the project life. The project electricity generation baseline may not stay constant through the life of the project due to factors such as changes in regulations in the electricity sector, the planned addition of new generation units on the grid, or decommissioning of existing units. For the purposes of the simplified analysis, we'll assume that the baseline does not change. The base case system or baseline system represents the system to which the proposed case system is compared. The base case system is normally referred to as the reference or baseline option in standard economic analysis. The values are calculated by RETScreen. The fuel consumption is given either in megawatt hours or gigajoules, and the GHG emission factor in kilograms of CO2 per kilowatt hour or in tons of CO2 per megawatt hour. The proposed case system or mitigation system is the proposed project. The proposed case system is normally referred to as the mitigation option in standard economic analysis. This small hydro facility does not have the vocation to serve large areas the way large gigawatt-scale nuclear or natural gas power plants do. One of the benefits of smaller distributed generation plants is that they can provide power to remote areas that are often close to the end of the line in a network. For this reason, the electrons of this type of project are likely to be used to serve the more local community, with the transmission losses falling on the lower end of the range given in the T&D losses section. Consequently, for electricity exported to grid, we'll enter 6% as a value for T&D losses. Based on the GHG emission data entered, the model calculates the annual reduction in GHG emissions when the base case system is displaced with the proposed case system. If the baseline for electricity production changes during the project life, the model calculates the annual GHG reduction for both periods of the base case, that is, for the years before the change in baseline and the years following the change in baseline. The GHG credits transaction fee cell is used to enter the percentage of credits that will have to be paid annually as a transaction fee. In order to obtain credit for a GHG project, a portion of the credits might have to be subtracted as a transaction fee to be paid each year to the crediting agency or the host country. For Clean Development Mechanism or CDM projects, 2% of the certified emission reductions or CERs generated by each project are to be paid into an adaptation fund to help particularly vulnerable developing countries adapt to climate change. Note that projects in least developed countries are exempt from this part of the levy in order to promote the equitable distribution of projects. The CDM Executive Board, as well as a number of host countries, also require that they receive a percentage of the credits to help cover their administrative costs. We may need to check the UNFCCC's CDM website and the host country's designated national authority to find out if they require a percentage of credits to be paid. The model then reduces the gross annual GHG emission reductions by this percentage to calculate the net GHG emission reduction. For this project, in order to evaluate the transaction fee, we would have to consider the origin of the possible GHG credits. There are two markets for carbon offsets. In the larger compliance market, companies, governments, or other entities buy carbon offsets in order to comply with caps on the total amount of carbon dioxide they are allowed to emit. This market exists in order to achieve compliance with obligations of Annex 1 parties under the Kyoto Protocol and of liable entities under the EU Emission Trading Scheme. In 2006, about 5.5 billion of carbon offset were purchased in the compliance market at an average price of $3.44 per ton of CO2. In the voluntary market, individuals, companies, or governments purchase carbon offsets to mitigate their own greenhouse gas emissions from transportation, electricity use, and other sources. For example, an individual might purchase carbon offsets to compensate for the greenhouse gas emissions caused by personal air travel. Many companies offer carbon offsets as an upsell during the sales process so that customers can mitigate the emissions related to their product or services purchased. In 2008, about 705 million of carbon offsets were purchased in the voluntary market, representing about $56.8 per ton of CO2 reductions. Offsets are typically achieved through financial support of projects that reduce the emission of greenhouse gases in the short or long term. The most common project type is renewable energy, which includes wind farms, biomass energy, or hydroelectric dams. Others include energy efficiency projects, the destruction of industrial pollutants or agricultural byproducts, destruction of landfill methane, and forestry projects. Some of the most popular carbon offsets from a corporate perspective are energy efficiency and wind turbine projects. Carbon offsetting has gained some appeal and momentum mainly among consumers in Western countries who have become aware and concerned about the potentially negative environmental effects of energy-intensive lifestyles and economies. The Kyoto Protocol has sanctioned offsets as a way for government and private companies to earn carbon credits that can be traded in a marketplace. The protocol established the CDM, which validates and measures projects to ensure they produce authentic benefits that are genuinely additional activities that would otherwise not be undertaken. Organizations that are unable to meet their emissions quota can offset their emissions by buying CDM-approved certified emissions reductions or CERs. As Canada has withdrawn from the Kyoto Protocol, there are no federal compliance GHG credits possible with that mechanism for this project. On the other hand, there are possible carbon exchanges that may be tapped into, where carbon credits are being traded in Europe, Chicago, and in Montreal. There is a global movement pushing for harmonization of the carbon markets. Ontario signed an agreement with Quebec in 2008 to develop a cap-and-trade system. In 2009, carbon prices traded at $6 per ton of CO2 equivalent in Chicago, $11 per ton in Montreal, and $26 per ton in Europe. Canadian government study predicted the price could increase to $60 per ton by 2018. As the price for a ton of carbon increases and the rules for trading become clear, it looks like opportunities may open up for Ontario Green Power to be part of the solution and potentially generate some revenues at the same time. From the perspective of the hydro plant investor, voluntary carbon offsets buyers are likely a more realistic, attainable, and cost-effective source to buy CO2 credits. Carbon credits in the voluntary markets are called voluntary emission reduction, or VERs, which are equal to 1 ton of CO2 emissions. For this project, we'll assume that voluntary carbon markets would be the most likely source of carbon credits. Voluntary markets registries take their share of the carbon price in the range of 5 to 30 US cents per VER. So, at $10 per VER, that would be 0.5 to 3%. We will arbitrarily pick a mid-range value of 1.5%. The model calculates the net annual reduction in GHG emissions estimated to occur if the proposed case is implemented. The calculation is based on the gross annual GHG emission reduction and the GHG credits transaction fee. Units are given in equivalent tons of CO2 emissions per year. The model allows us to compare the net annual GHG emission reduction with units that are easier to conceptualize. These numbers are based on North American energy patterns and are published by the U.S. Environmental Protection Agency. Note that RETScreen rounds the numbers such that 1.5% shows up as 2% as illustrated here. Using the various net annual GHG reduction values, we will get the following equivalencies for the 1,187 ton annual CO2 emission reduction. We can use a drop-down list to select a value that is suitable for the reader of the report. For example, if the audience does not relate well to how large a barrel of crude oil is, it is better not to use that and instead use something that will allow the user to make a logical comparison. Let's now click on the next tab to access the financial analysis worksheet. When using the general analysis type of method 2 for a hydro project, this cell would be used to enter the fuel cost escalation rate, which is a projected annual average rate of increase in base case and proposed case fuel cost over the life of the project. As the grid type has been set to central grid, the base case does not include the generator, which would require fuel. So any value in this cell would have no impact on any of the financial parameters. Note that if the grid type has been set to another option, especially the off-grid type, this would be the value of the rate of inflation to fuel cost, which might be different from general inflation. For example, in North America, long-term fuel cost escalation rates range anywhere from 0 to 5%, with 2 to 3% being the most common values. In this project, the fuel cost escalation is not applicable. We'll leave it blank or set it to 0%. This cell is used to enter the inflation rate, which is the projected annual average rate of inflation over the life of the project. For example, inflation from the 25 years after 2012 in North America is typically forecasted to range between 2 and 3%. This rate has an impact on both annual cost and various costs that may incur after the project is commissioned and during its life cycle. In the context of a hydro project, we have evaluated the following annual and periodic cost. Without taking inflation into account, the annual cost represents $4.08 million versus $0.275 million for the periodic cost. The annual costs represent about 93% of the total operating cost, and of all that, about 2/3 are attributable to parts and labor, and the balance is mostly attributable to lease costs. Compared to the initial cost of $2.92 million, we can appreciate that any increase over the annual cost will have a huge impact, as the maintenance cost represents about 1.3 times the initial cost without inflation. Therefore, variations of inflation will have a large impact on the project's financial performance. It is very difficult to predict the long-term inflation rate for any country. Even armies of financial analysts at central banks cannot predict accurately more than a few months or a year ahead. Many factors come into play, including national and international political, economic, and weather events. Assuming fairly stable conditions and based on a simple extrapolation of recent trends, we'll assume inflation to stay in the 3% range. But it is possible that inflation could become null or negative, or return to the high values of the 1970s and 1980s and average 6 to 9% over 20 years. A negative inflation is called deflation. Deflation is a decrease in the general price level of goods and services. Deflation increases the real value of the currency of a national or regional economy. This allows one to afford more goods or services with the same amount of money over time. Economists generally believe that deflation is a problem in a modern economy because it may aggravate recessions and lead to a deflationary spiral. Historically, not all episodes of deflation correspond with periods of poor economic growth. Deflation occurred in the US during most of the 19th century. This deflation was caused by technological progress that created significant economic growth. This deflationary period of considerable economic progress preceded the establishment of the US Federal Reserve and its active management of monetary matters. Japan has recently experienced a decade of deflation, which likely relates to the government's focus on exports. Canada could also focus on exporting its resources and trigger deflationary policies to support its natural resources. It is important to understand that if a significant portion of a project's cost during the operation related to some equipment imported from another country, then we would have to prorate the inflation with the inflation of that country. In our case, less than 2% of the costs are estimated for the turbine and generator replacement. So even if these parts were imported, about 98% of the project would be domestic and therefore would be affected by the Canadian inflation rate. For this project, we will use a moderate 2%, even though there are many inflationary pressures ahead, such as government debts, depreciation of the Canadian dollar, increase in population through immigration to Canada, increase in prices of food, oil, and others. This cell is used in RETScreen Analysis type of method 2 to enter the discount rate, which is the rate used to discount future cash flows in order to obtain their present value. The rate generally viewed as being most appropriate is an organization's weighted average cost of capital. An organization's cost of capital is not simply the interest rate that it must pay for long-term debt. Rather, the cost of capital is a broad concept involving a blending of the cost of all sources of investment funds, both debt and equity. The discount rate used to assess the financial viability of a project is sometimes called the hurdle rate, the cutoff rate, or the required rate of return. The model uses the discount rate to calculate the annual life cycle savings. For example, North American electric utilities currently use discount rates ranging anywhere from 3 to 18%, with 6 to 11% being the most common values. For this project, we will assume a discount rate of 8% to reflect a modest amount of risk associated with the project type. This cell is used to enter the project life, which is the duration over which the financial viability of the project is evaluated. Depending on the circumstances, it can correspond to the life expectancy of the energy-related equipment, the term of the debt, or the duration of a power purchase agreement. The model can analyze project lives up to 50 years. Even though hydro projects may have a much longer lifespan compared with other renewable energy projects, a project life equal to the power purchase agreement is preferred by financial institutions that provide debt financing. As the FIT contract would be for 40 years, we will select a project life of 40 years. This cell is used to enter the financial incentives, which are any contributions, grant, subsidies, or other funding that is paid for the initial cost of the project. In the model, the incentive is deemed not to be refundable and is treated as income during the development year, year zero, for income tax purpose. If an incentive is paid over a number of years, it can be entered in the other income section. The incentives and grants are transferred to the project costs and savings and income summary section. We have no reason to believe that there are any incentives available for this project and will thus enter 0 in the incentive cell. The debt ratio is the ratio of debt over the sum of the debt and the equity of a project. The debt ratio reflects the financial leverage created for a project. The higher the debt ratio, the larger the financial leverage. The model uses the debt ratio to calculate the equity investment that is required to finance the project. For example, debt ratios typically range anywhere from 0 to 90%, with 50 to 90% being the most common. For this study, we'll assume that 80% of the project will be financed. This cell is used to enter the debt interest rate, which is the annual rate of interest debt to the debt holder at the end of each year of the term of the debt. The model uses the debt interest rate to calculate the debt payment. For example, at a minimum, the debt interest rate will correspond to the yield of government bonds with the same term as the debt term. A premium is normally added to this rate to reflect the perceived risk of the project. The project proponent has prearranged financing at a 7% interest rate due to the perceived level of project risk. This cell is used to enter the debt turn, which is the number of years over which the debt is repaid. The debt turn is either equal to or shorter than the project life. Generally, the longer the term, the more the financial viability of an energy project improves. The model uses the debt turn in the calculation of the debt payment and the yearly cash flows. The term of the debt normally falls within 1 to 25-year range. It should not exceed the estimated project life. Typically, commercial loans from banks do not exceed 8 to 12 years, but energy projects can be treated differently. In a way, these loans are more like mortgages, and therefore longer terms can be negotiated. Just like with the debt ratio, increasing the debt term will increase the annual cost and global cost of the project. Increasing the IRR on equity, but reducing the payback and the IRR on assets. The pre-arranged financial plan allows for a debt term of 20 years. For the purposes of this simplified study, we will not enter income tax values and leave this box unchecked. Subsequent studies can be expected to go over the income tax analysis in detail. If there is electricity exported to the grid by the proposed case power system, certain input fields will be added to allow us to customize the electricity export income analysis according to the specified circumstances of the project. The model automatically calculates the values apart from the escalation rate. It shows that 2,628 megawatt hours can be produced each year using data from the energy model. The electricity export rate of $131 per megawatt hour is the rate that we entered previously in the energy model. The electricity export escalation rate is the projected annual average rate of increase in the electricity export rate over the life of the project. This permits us to apply rates of inflation to the value of the electricity export rate, which might be different from general inflation. Under the Ontario FIT contract offered at the time of this project was examined, water power projects were allowed to escalate 20% of the contract with the Ontario Consumer Price Index, or CPI, from the time the project reaches commercial operation through the length of the contract term. The CPI average is equal to 2% times 20% escalation, or 0.4%. The completed financial analysis should now look as shown here. Looking over the results, we can see that the project feasibility is in question for a hydropower project. The financial returns are marginal, offering an IRR of 8%. The simple payback is 12 years, and equity payback is 23.4 years, which means that the debt provider might not want to finance the project. A further look at the financial return shows us that the NPV is also negative. Looking at the net benefit cost ratio, we see a value of 1. The net benefit cost ratio, similar to the profitability index, leads to the same conclusion as the net present value indicator. Ratios greater than 1 are indicative of profitable projects. This indicator, along with the debt service coverage, is a ratio used extensively by potential lenders for a project to judge financial viability and risk. For this project, it is 0.61, while a ratio of 1.5 is usually seen as the minimum. The project proponent would therefore be able to conclude from this analysis that the project is marginal and might not be able to qualify for financing. Let's look at the impact of possibly obtaining a GHG credit thanks to VERs. We will assume a 40-year net GHG reduction. As we can see, the more GHG credits the project is able to obtain, the better the project viability becomes. A more detailed analysis may result in the real possibility to obtain credits in the range of $2 to $30 per ton, with a more probable number being in the area of $9 per ton. But at this time, we'll leave the GHG reduction credit blank. Here we can see the complete financial analysis worksheet.